Yeah, so what I will talk about in this session is basically I'll answer two questions. The one question was your question, where's speech? I'll talk about speech, and I will try to get away from text as quickly as possible. Then you will not see any text in the rest of the talk. And then I will answer someone at the back, ask the question, what do I do if I have a language where we've got a lot of spoken data, but we don't have anything else? We can maybe get speech data in a way, but apart from that, we don't have anything. What can we do in settings like that? Yeah, so I entitled the talk Outrageously Low Resource Speech Processing. I can't remember if Jade actually used the word outrageously somewhere in her talk, but she's a bit outrageous. So I just put that in my title. Okay, so we've heard a lot about text processing, but I'll talk about speech. And some of you might know this is not the Amazon, this is the other one from the small software company. You are coming up for the little guy. It's really exciting time if you're a speech recognition person. People are actually starting to use speech systems in their homes, right? And yeah, this is one example of that. How do Google or other companies, how do they build speech recognition systems? Alexa and Google Voice, how do they build these systems? They get a lot of data where you have the audio waveform at the top there, and then someone carefully goes and transcribes exactly what is being said in that sentence. Okay, and if you have paired data like that, where you have speech and the words at the bottom, then you can train one of your fancy sequence-to-sequence models to take that speech and translate it into words. Okay, so you go from speech to text. The problem with this, of course, is that it takes a huge amount of effort to collect the transcriptions. And at the Apple event last night, which was amazing, they said they already cover 35 languages. I think Google covers a little bit more. So it's quite exciting, but we speak 2,000 languages just on this continent. And if we're going to build speech systems for all those languages, then I think this paradigm is going to be super problematic. What I work on is something called unsupervised speech processing. Some people call it zero-resource speech processing. And this is basically the problem of asking, what can we learn if we do not have any labels? We don't have any text. Specifically, the question is, what happens if I give you a corpus of speech audio, just the audio? I don't tell you what language it is. I don't tell you the words that occurs in this language. Basically tell you nothing apart from that this is speech. And the question is, what can you learn just from this audio? And if we could solve this problem, it would be very useful, because in a lot of settings, it's much easier to just collect speech audio than it is to actually transcribe it. So there's projects, for example, scraping broadcast news. So as things are being broadcast, you just record that audio, and then that way you can collect a relatively large set of unlabeled speech. And what zero-resource speech processing tries to solve is tasks like, for example, figuring out what are the minimum set of units, the smallest set of units that's used in this language. What are the phonemes that are used in this specific language? And you want to try and do that just from the speech audio, no text. We're away from text, no text again in this talk. Or you might want to figure out what are the words used in this language. You might want to look at this signal and say, I want a model that can predict that the word starts here and ends here, and the next word starts here and ends there, and then so on, okay? That's called segmentation. I might want to figure out what's the lexicon, what are the words actually used in this corpus. Figuring out things like where do words start and end is very, very hard. We think it's easy, but if you don't know a language, we think of it as these discrete, like little symbols going together, and that there's little pauses. But there's actually, if you look at speech, there's very few pauses between words. So it's a very hard problem. So if we can do this, if we can, number one, figure out kind of at the short time span, what are the units in the language? And then also at the longer time span, figure out how to chunk up the speech into word-like units. then we can build useful downstream tasks on those type of tokenizations. So zero resource people, they look at two problems really. Short time span things, often sometimes they call it unsupervised representation learning, trying to figure out what are the useful features at the short time span. And then the second task that they often work on is kind of breaking it up into longer spanning things, maybe breaking it up into phrases or words. A lot of speech recognition people tell me this is really not useful, this is not something that anyone will use. But I want to give you an example. This is work from one of my PhD advisors, of an actual useful speech processing system that doesn't have any text. Okay, so imagine we scraped a corpus of Swahili broadcast news, we plump a server somewhere, and we're just recording the radio broadcast that goes into that, and we don't have a Swahili speech recognizer. What we can then do is we can build a system, or develop a method, where a person phones into the system, they say a word, so you have a spoken query, they say a word, and then what you want to do is, you want the system to go and find all the news reports containing that word somewhere. Okay, it doesn't do there's no text anywhere, it just tries to do this matching task. This is called query by example search, and it's an example of actually a useful information retrieval type system that you can develop without any text anywhere. Okay, so when I talk about outrageously low resource, maybe the most outrageously low resource is a completely zero resource, okay, or unsupervised. I will talk about three things very, very quickly. I will try to convince you that this is basically the most interesting problem you can ever work on. I will try to kind of really tell you that this is a fundamental machine learning problem. I will try and, the second thing is I will try to tell you some of the key ideas which I think is needed to solve this problem, and then finally I will tell you what I think is missing. Like what are the core things that we need to look at. Okay, so why is this problem important? Like I mentioned, there's really two things that people look at in unsupervised speech processing. It's learning things at the short time frame. That's really unsupervised representation learning. And you want to learn these representations from unlabeled speech. And then the second thing is segmenting, clustering, and discover longer spanning things. And it's a super difficult problem because it's unsupervised, but it glues together very fundamental things in machine learning. You need to solve the perception problem. How do we perceive speech sounds? That's very, very tricky. We know that speech, which is a form of language, has structure, and we need to model that. And what makes speech specifically difficult is that it's a continuous signal, but we know that there is discrete units somewhere. So it's this combination of perception, structure, continuous, and discrete variables. Okay. But I think it's probably the coolest machine learning problem that you can work on. And one reason I'm saying this is that if you go and look at these machine learning textbooks, so it's Murphy's book, ESL, and Bishop's book, which are kind of some of the best textbooks in machine learning. If you go and read how they define machine learning, I'll just read Murphy's one. The goal of machine learning is to develop methods that can automatically detect patterns in data. Okay, Bishop says somewhere the problem of searching for patterns in data is fundamental. Okay, and this is actually, I cherry-picked this. Okay, it is in these books, but I put those dots in selected places to make my point. But if you read this is actually so far from supervised problems, right? Trying to find patterns automatically in data, I think it's just a very, very powerful. If we could do that, we could solve a lot of problems, and I think unsupervised speech processing is one way to do this. Okay, so this is the number one reason this is amazing. The second reason I think this is very, very important is that if we could solve this, we could build universal speech technology. So I have this quote, imagine a world in which every single human being can freely share in the sum of all knowledge. So I stole that from Laura, who sent it to me in an email, but she stole it from the Wikimedia Foundation. Anyway, so I think it's a very, very, very cool and powerful mission statement. And if we could learn just from raw audio, I think we could really tackle this. I'm going to give you some quick examples of people who have tackled this type of problem. So this is work done by people at Stellenbosch and Makerere University in collaboration with the United Nations. So what they worked on is this system. So the United Nations are particularly interested in basically developmental monitoring. So they have a lab in Uganda, and they want to know what people talk about on local radio shows. Because local radio there is one way in which people communicate. You phone in and you tell a story, you speak about what concerns you. And what the UN is interested in is they want to know what people are talking about. So they have these lists of keywords that they want to spot in the data. The problem in Uganda is you have a lot of different languages. So traditional speech recognition is actually very, very difficult. So how their system works, basically it records broadcast news, and conventionally what you would do is you would run it through a speech recognition system and then do keyword search. Turns out this doesn't work really well. Okay, the whole system, you basically flag a keyword and that gets passed on to a human analyst who feeds it into a database, and the database ultimately tells the United Nations what are people talking about, what are their concerns. Are there things like a disease outbreak taking place in a specific area that people are talking about on that radio show? The problem is, for a lot of these languages, you don't have speech recognition systems. So what they try and do is they try and do this kind of more brute force way where you build a keyword spotting system using almost no resources, and they use some of these ideas from zero resource speech processing to do this. And I'll talk about those ideas. I'll skip this one because I'm always slow. Another example application, so this is a picture of Stephen Bird. He used to be in Australia. He is really, really passionate about actually documenting and preserving endangered languages. And for a large number of endangered languages, there isn't even a written form. So a lot of these languages, you can't even write down what's being said because there isn't a writing system. And if you want to preserve these languages or process speech in that language, then there isn't any text to work with, right? So what he does is he asks, specifically he asks native speakers of some of these endangered languages to tell stories in their language. And normally these speakers are bilingual, so they also then tell the stories in English or some other kind of well-resourced language. If we can solve unsupervised speech processing, we can help these guys that's trying to really preserve dying languages and document them. Okay, this is something that I find super exciting. So a third reason to look at unsupervised speech processing. Humans, infants, when they learn language, don't see any text ever, right? But by 4 years old, after being bombarded with some speech data, they're actually amazing speech recognition systems, right? And you can take an infant, you plump them in an environment, leave them to train for 4 years, and after that, they're pretty good speech recognition systems. They're better than a lot of the speech systems we have. And so one reason to look at unsupervised speech processing is that we do know that infants do use the unlabeled data that they acquire. They use that somewhere. And there's actually a whole field of, in kind of the NLP world, that looks at cognitive modeling. These are people that's really interested in actually figuring out how do humans learn language. How do we as humans learn language? And the argument goes something like this. If you have a model that learns language in a similar way to humans, not exactly, but a similar way at kind of a software level, not at the neuron level, but at the software level, a model that uses the same mechanisms and principles as a human. If we had a model like that, then we can probe this model really well, right? We can do different experiments on this. We can answer questions like, what happens if I bombard this model with 5 languages instead of just 1? And these are experiments that you might not want to do on infants. Right? You don't want to do these control tasks where you speak a lot to one baby and not to another one. But if you had a model which you can probe, if you had a cognitive model that's accurate, then we can probe it and find out how the underlying mechanisms. But for that, you need an accurate model, which we still don't really have. But unsupervised speech processing is going that way. And if we could do that, we could really start to develop applications like figuring out when infants, so this is a project actually from, so Okko Rusanen is working on this, is a researcher. They're trying to do things like figure out how much do parents speak to their children and how important is that. If you could have a very accurate cognitive model, you could start to figure out by which stage should infant have learned certain things. And in that way, you can start to predict learning difficulties early in life. You can do things like predict hearing loss, if we could basically track how infants learn. Okay, infants don't learn just from speech audio, and I'll say something about that in 3 slides. Okay. So those were 3 big reasons for why I think this is an important thing to work on. 3 ideas to tackle these problems. I think the biggest idea, if we want to solve this, is that we need to figure out ways to build domain knowledge into models. So we know a lot about language, and we can build that into models. People call this by different names. You need to figure out how to kind of put an inductive bias into your model, or a Bayesian prior, or regularize, or use data augmentation to allow these unsupervised models to learn what you actually wanted to learn. And we do know a lot about languages already. Linguists have studied language for thousands of years, and the question is, how can we build in some of that information into our unsupervised models? As a very concrete example, if you're processing kind of a zero-resource language, if you just have speech audio that's just coming in, okay, and it's in this language that we don't have any label data for, that's true, but we do know a lot about other languages. So we actually have a lot of resources for English, German, Spanish, and those type of languages. And the question is, what can we learn from those languages for which we have a lot of data, which we can then apply to these zero-resource languages? So as a very quick example, what these researchers did was they trained a supervised speech, basically speech recognition system. That's not exactly correct, but something close to it, on Korean, German, and French, for which they do have data. They then cut the network somewhere in the middle, and then they take intermediate representations from there. That's now your new features that you're going to use to process the speech. And what they then do is they feed Tsonga speech into the bottom of this model, and they use the features that's kind of learned across these well-resourced languages. They use these features in downstream tasks for Tsonga. So they use information from German, Korean, and French, but then use it to process Tsonga speech, which I think is pretty cool. Okay, so some graphs. A second idea I think that's super important is compression. This is somewhat different from the Apple talk where they talked about model compression. Here I really talk about data compression. And we as humans actually are excellent compression systems. Later tonight, when you think back of Richard Soker's talk this morning, you won't remember exactly the words he said or the phrases he used or the pitch of his voice, but you've already compressed his talk in some way into some representation in your head. And you don't remember everything, but you have the semantics in there. And that's actually an extreme form of compression, and I think it's really important to build that into our models. So most of you will probably know about autoencoders, and this is kind of the most basic neural network that does compression. I mean, it's almost an extension of PCA, but you have the input, you pass it through some feed-forward layers. You have a hidden vector that's probably, well, normally lower dimensional than your input, and then you try and reconstruct that input on the output side. And by doing this, you're basically compressing this relatively high dimensional input into a lower dimensional space. Okay, that vector is still continuous. There's actually still a lot of information in there. So something that I'm personally very excited about is this idea of discretizing that middle representation. And this is a very extreme form of compression. So a very popular way to do this is vector quantized variational autoencoders. This looks very similar to an autoencoder. So you take your input, you're going to compress it, I'll talk about that in a second, and then you're going to kind of decode it into the original image. Okay? And what you're going to try and do is you're going to try and learn this thing so that what you put in is also what you get out. Okay? So a normal autoencoder has that narrow middle layer. What makes a variational autoencoder different is that you can only pick, for your kind of hidden vector, you can only pick one from a set of codebook vectors. So how the model works is it has a little dictionary. And what it says is, when I feed my input in, I map it to some continuous vector, and then what I will do is I will select from this codebook, I will select the closest one, okay? And then I will put that here and I will decode from that. And in contrast to a normal autoencoder, we can have any vector here. Now this vector needs to be one from a set of k. And it's a very nice way to discretize your inputs, to really make it discrete. I'm running out of time, but I quickly want to just play some of the examples that we did in our own group recently. A number of students worked on this project, 10 students to be exact, but I'm just highlighting 2 that couldn't be here, and they put a lot of effort in this. And Ryan is the other one who's somewhere here, I hope. So what we did was we took part in this challenge, and the challenge went something like this. You get a large corpus of unlabeled audio, and from that you need to discover the units that's used in that language. Once you've discovered those units, okay, so you have a large corpus of audio, we train this vector quantized variational autoencoder on that audio, and from that we discovered the units. Okay. Now you've got units, nice. What can you do with those units? So one thing you can do is you can actually use those units for speech synthesis. So what we will do is we will feed in an utterance that the model has never seen. We will figure out the units in that utterance. And then what we will do is we will synthesize from those units, we will synthesize the output. So I'll play you, that maybe doesn't make all that much sense, but you can come and chat to me afterwards. But I'll try and play you some examples. So the input to this model.
It is a part of his genius.
Can you hear that? Okay.
It is a part of his genius.
So that's an input the model has never seen. He's never seen this, the model as he or she never saw the speaker. Okay, and this is the output from the model. So what we do is we take that input, we find the units that, according to our model, is the basic building blocks of this language. And then from those units, we're now going to synthesize. Okay, we're going to see, like, how does that sound? Okay, and this is the output.
It is a part of his genius.
Okay, so it's not perfect, but we've basically built a speech synthesis system without any transcriptions, any text. Okay, here's Indonesian, which was the surprise language. It was part of the challenge. We didn't know this was it. It doesn't sound as great, but I'll explain it to you now.
Dalam posisinya yang relatif netral.
Input.
Dalam posisinya yang relatif netral.
That's the output. It doesn't sound great, but you can actually make out what she's saying. The reason this doesn't sound so great is because the input we fed in was a male voice, and then we tried to synthesize it in a female voice. When it was female-female, it sounded a lot better. Okay. The third, I'm running out of time, I know you're not. The third kind of core idea I think that will help us solve this problem is learning from multiple modalities. So infants don't just get bombarded with speech audio. They learn in context, right? They also learn through interaction. But one specific thing we're focusing on, and other people are also focusing on, is this idea of learning when you have speech, but you have the visual context that's paired with that. So in this example, this is speech. It's a little spectrogram. You don't know what's being said. You don't know the text associated with this. But what you do know is that this spoken utterance occurred in this context. So it occurred with this image. And what David Harworth, Jim Glass, it's a group at MIT, what they're trying to do is they're trying to see what can you learn when you have speech paired with an image. Okay? And it has basically 2 motivations. The one is to better understand human language acquisition. But the second reason is when you're documenting a language that doesn't have a written form, this might be one way to kind of capture what's going on. So you can show people in that, speaking that language, you can show them pictures and ask them, explain this picture, describe this picture with your own voice. And from that, try to build some speech processing system. And we found, and they've also found this, that this often works better than just the purely unsupervised case. So here you're trying to glue these things together. I'll quickly mention work by Ryan and Leanne. So what they're working on is this idea of, in a one-shot way, learning from images and speech. This won't make sense because I'll have to explain it in 30 seconds. But basically the idea is if you have an image, so this is an image, and you have a spoken snippet that goes with that image, can you from one single example learn this mapping between speech and image? Okay? Yolanda, I know I'm out of time. So the idea is something like if I had a robot in my house and I showed it an object, a visual object, and I called it, I don't know, pisang, which is the Afrikaans word for banana. I show it the pisang, I show it the apple, I show it the lemoen, okay? And I show it just one example of this visual object, and I said the name. Can the robot learn the mapping, the direct mapping between the speech and this visual object, just from one or maybe 5 examples? I messed that up, okay, but you get the idea. Okay. Okay, I'll wrap up by saying what I think is still missing. I think there's major engineering and technical challenges still missing, specifically for how we can build kind of common sense, or if we know a lot about language, but it's not that easy if you have a neural network to just kind of build in that information. Even before with Bayesian models, it wasn't always obvious how you use the priors to kind of put in the information you have. So I think we need to figure out generic ways to incorporate domain knowledge in these models. Scientifically, I think there's still a lot of work about how we as humans learn language, because if we understand that, we can build that into our models. This is a core point that I also spoke to some of you about. What are useful practical applications that we should be working on? And this is something I'm really guilty of. I normally get all my ideas in the shower. So I stand in the shower and then I'm like, oh, wow, that's a really cool thing that maybe my model can do, right? And then I go and I try and do it and try to write a paper, okay? But I often forget about asking, like, is this actually useful? What are the actual problems that someone is struggling with? And how can the expertise that I have actually help that person? So I think that's a major part that's at least missing in my life, okay? So instead of just spending time in the shower, you need to figure that out, okay? And related to that, real test cases on real low-resource languages. We need impactful stuff that's actually making a change. I'm going to show you a quote from a reviewer that rejected a paper that I was involved with, and I completely agree with this statement. So the reviewer said, while the authors did make an effort to artificially limit the data availability, I don't think the main claims of this paper is generalizable to actual low-resource languages. And I think this really hit home, right? So we need to figure out what are the places where we can really address practical problems that people have, and then we need to go and address it, okay? And for that, we obviously need data, which I think we heard a lot about. Okay, that's it. I'll just take one question, but I will be here, so.
I just want to know, can you generalize this model for accents?
No. She asked about accents, which is actually quite complicated. Accents is kind of almost like a nuisance variables in some cases. I did my master's on accents of South African English, and that was really, really difficult because in South Africa we have 5 different accents of English, and of course you're on a spectrum with these accents. Like especially younger South Africans don't speak like kind of one specific accent. And the problem there, of course, is data. If you know which accent is being spoken and you have labeled data in that accent, then you can do something about it.